7.4. Energy of orbital. The energy of an electron in the hydrogen atoms or hydrogen-like species is determined by the principal quantum number alone. This is because the only interaction in these species is attraction between the electron and the nucleus. An increasing order of energy of orbital in the hydrogen atom is given by 1s smaller than 2s equal to 2p smaller than 3s equal to 3p equal to 3d smaller than 4s equal to 4p equal to 4d equal to 4f smaller and so on. Of course, the shape of the concerned s, p, d, f orbitals are different, as described earlier. The orbital with the same energy and the corresponding wave function being different are called degenerate orbitals. Thus, in hydrogen atom, 2s and 2p are degenerate orbitals. In multi-electrons atom, there is a mutual repulsion among the electrons. The energy of an electron in a multi-electron atoms therefore depend both on the principal quantum number n and azimuthal quantum number l. The lower the sum n plus 1 for an orbital, lower is its energy. If two orbitals have the same n plus 1 value, then orbitals with lower value of n is of lower energy. This is called n plus l rule. From the n plus l rule, the increasing order of energy of orbitals in multi-electron atoms can be written as 1s smaller than 2s smaller than 2p smaller than 3s smaller than 3p smaller than 4s smaller than 3d smaller than 4p smaller than 5s smaller than 4d smaller than 5p smaller than 6s smaller than 4f smaller than 5d smaller than 6p smaller than 7s. See table 4.9. Table 4.9. Dependence of orbital energy on n plus l value. Orbital energy 1s. Principal quantum number n equal to 1. Azimuthal quantum number l. L is equal to 0. N plus 1 is 1 plus 0 equal to 1. Orbital energy 2s. N equal to 2. L equal to 0. 2 plus 0 is equal to 2. 2p n equal to 2, l is equal to 1, 2 plus 1 equal to 3, n equal to 2, lower, 3s, n equal to 3, l is equal to 0, 3 plus 0 equal to 3 is n equal to 3, higher, 3p, n equal to 3, l equal to 1, 3 plus 1 is 4, n equal to 3, lower, 4s, n equal to 4, l equal to 0, 4 plus 0 equal to 4, n equal to 4 is higher, 3d, n equal to 3, l equal to 2, 3 plus 2 equal to 5, n equal to 3 is lower, 4p, n equal to 4, l equal to 1, 4 plus 1 equal to 5, n equal to 4 is higher. In a multi-electron atom, electrons occupy different orbitals. The lowest total electronic energy corresponds to the most stable, that is the ground state of an atom. The orbital-wise distribution of electrons in the ground state can be understood from what is called the Aufbau principle. 4.7.5. Aufbau principle. Aufbau is a German word meaning building up. This building up of orbitals means filling up of orbitals with electron in the ground state of an atom. The Aufbau principle is based on first, increasing order of energy of orbitals, second, Pauli's exclusion principle, and third, Hund's rule of maximum multiplicity. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7f, 7s, 5f, 6d, 7p, 6f. First, the increasing order of energy of orbitals. As seen in section 4.7.4, the increasing order of energy of orbitals is decided by n plus L value. Electrons in the ground states atoms are filled in the orbiter in an increasing order of energy. Figure 4.10 show a useful method to remember this increasing order of orbital energy. Second, Pauli exclusion principle. The capacity of an orbital to accommodate electron is decided by Pauli's exclusion principle. Wolfgang Pauli 1926 recognized that no two electrons in an atom can have the same set of four quantum numbers. Another way to state this Pauli exclusion principle is only two electrons can occupy the same orbit and they must have opposite spin. Pauli exclusion principle imply that for an electron belonging to the same orbital, spin quantum number ms must be different since the other three quantum number n, l, m are the same. There are only two values that ms can, which are plus 1 by 2 and minus 1 by 2. An orbital thus can accommodate only two electrons with opposite spins, so that the fourth quantum number is different for two occupying electrons. These two electrons with opposite spins occupying the same orbitals are called an electron pair. This principle is illustrated with helium atom helium Z equal to 2. Its electronic configuration is 1s2 as and two electrons are in 1s orbital. The two non-identical combination of four quantum number of both electrons in helium are given in 4.10. Electrons. First electron quantum number n is 1, L is 0, Mn is 0, Ms is plus 1 by 2. Set of value of four quantum number is 1, 0, 0 plus 1 by 2. Second electron n equal to 1, L equal to 0, Ml equal to 0, Ms is minus 1 by 2. Set of value of four quantum number is 1, 0, 0 minus 1 by 2. It implies that two electrons in the same atoms have always different set of quantum number. That means the set of n, l, ml is the same and the ms is different. Since an orbital can accommodate up to two electrons, only the capacity of a shell with the principal quantum number n to accommodate electrons given by 2n square. Third, Hund's rule of maximum multiplicity. Filling of electrons in orbitals belonging to the same subshells. Orbitals of equal energy or degenerate orbital follow the Hund's rule of maximum multiplicity. As per this rule, pairing of electrons in the orbitals belonging to the same subshell does not occur unless each orbital belonging to that subshell has got one electron each. Consider, for example, filling of p subshells. The p subshell has three generate orbitals. Their pairing of electrons start when the fourth electron enters the p subshell. The electron configuration of four electrons occupying p orbital then will be and nor as means each orbital should be filled by one electron. If extra electron is remain, then it should be filled from the first position where one lone pair electron is already present, and not in this way. Means from the first orbital, two electrons shouldn't be filled. It should be filled from first orbital. It should be filled as one lone pair of one uh, unpaired electrons, and then it should be paired once all the orbitals is filled with unpaired, unpaired electron. It is observed that half fields and fully filled set of degenerate orbitals has extra stability. 4.7.6 Electronic configuration of atom and its representation. Electronic configurations of an atom is a distribution of its electronic orbitals. The electronic configuration can be written by applying of Bohr principle. There are two methods of representing electronic configurations. First, orbital rotation NSA, NPB, NDC. Second, orbital diagrams. In the orbital's rotation methods, a shell is represented by the principal quantum number followed by respective symbol of a subshells and number of electrons occupying that subshells being written as superscripts on right side of the symbol. In the orbital diagram method, each orbital in a subshell is represented by a box and the electron represented by an arrow for up and for low spin. For up spin and for low spin. Up spin uh, that is towards upward direction and low spin that means the arrow is towards down direction. Place in the respective power in this method. In this method, all the four quarter number of electrons are accounted for. Electronic configuration of a few elements is illustrated in table 4.11. Table 4.11 representing of electronic configurations. Element symbol 1H orbital notation 1s1 orbital diagrams. 2 helium 1s2 1s orbital having 2 electron. 3 lithium 1s2 2s1 1s2 electron 2s1 electron. Beryllium 4 1s2 2s2 1s having 2 electron 2s having 2 electrons. 9f 1s2 2s2 2p5 1s have one pair of electron, 2s has one pair of electron, 2p has three pair of electron. Consider orbital notation of electronic configurations. The orbital notation of electronic configurations of an element with a higher atomic number comprises a long trains of symbol of orbitals with an increasing order of energy. It can be condensed by dividing it into two parts. Electronic configurations of the preceding inert gas is a part of the electronic configurations of any elements. In the condensed orbital notation, it is implied by writing symbol of that inert gas in a square bracket. It is core part of the electronic configuration of that element. The outer configuration is specific to particular element written immediately after the bracket. For example, the orbital notation of potassium K Z equal to 19 is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Its core part is the electronic configurations of the preceding inert gas argons AR 1s2, 2s2, 2p6, 3s2, 3p6, while 4s1 is an outer part. Therefore, the condensed orbital notation of electronic configuration of potassium is K argon 4s1. Table 4.12 display detail and condensed orbital notation of electronic configuration of various elements with atomic number from 1 to 30. Internet, my friend. Visit following link, download the information and make a presentation. www.thoughtco.com/definition. Electronic configurations of copper and chromium Cr. Atomic number of chromium is 24. Expected electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. In that case, 3D is not half-filled, hence it has less stability. Inter-electronic repulsion makes one 4s electron enter into one of empty 3D orbitals. Thereby, both 4s and 3D orbitals become half-filled so that Chromium atoms require extra stability. Its electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Copper. Atomic number of copper is 29. The expected electronic configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. Here 3d orbital is neither half filled nor fully filled due to inter-electronic repulsion force. 1 4s electrons to enter into 3d, which make it completely filled with 4s being half filled. Hence, copper atom require extra stability. Now, electronic configuration of copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. Isoelectronic species. Atoms and ions have the same number of electrons. Are isoelectronics. The electronics configuration of isoelectronic species is the same. Consider K plus formed by removal of one electron from K atoms, which has 19 electrons, Z equal to 19. Therefore, K plus has 18 electrons. Number of electron. K is equal to Z 19 gives K plus plus electron. 19 is potassium, K plus is 18. Species such as argon, calcium 2 plus containing 80 electron are isoelectronic with K plus. Electronic configurations of all these species with 80 electron is 1s2, 2s2, 2p6, 3s2, 3p6. Electronic configuration of the first 30 elements. Atomic number 1, hydrogen 1s1. Condensed notation of electronic configuration is 1s1. 2, helium 1s2, 1s2. 3, lithium 1s2, 2s1, helium 2s1. 4, beryllium 1s2, 2s2, helium 2s2. 5th, boron 1s2, 2s2, 2p1, helium 2s2, 2p1. 6, carbon is 1s2, 2s2, 2p2, helium 2s2, 2p2. 7, nitrogen 1s2, 2s2, 2p3, helium 2s2, 2p3. 8, oxygen 1s2, 2s2, 2p4, helium 2s2, 2p4. 9th, fluorine 1s2, 2s2, 2p5, helium 2s2, 2p5. 10th, neon 1s2, 2s2, 2p6, helium 2s2, 2p6. 11th, sodium 1s2, 2s2, 2p6, 3s1. Neon 3s1. 12th, magnesium 1s2, 2s2, 2p6, 3s2. Neon 3s2. 13, aluminum 1s2, 2s2, 2p6, 3s2, 3p1, neon 3s2, 3p1. 14, silicon 1s2, 2s2, 2p6, 3s2, 3p2, neon 3s2, 3p2. 15, phosphorus 1s2, 2s2, 2p6, 3s2, 3p3, neon 3s2, 3p3. 16, sulfur 1s2, 2s2, 2p6, 3s2, 3p6, neon 3s2, 3p4. 17, chlorine 1s2, 2s2, 2p6 is 3s2, 3p5, neon 3s2, 3p5. 18, argon 1s2, 2s2, 2p6 is 3s2, 3p6, neon 3s2, 3p6. 19, potassiums 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, argon 4s1. 20, calcium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, argon 4s2. 21, scandium 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. 4s2 argon, 4s2 3d1. 22 titanium, 1s2 2s2 2p6 3s2 3p6 3d2 4s2 argon, 4s2 3d2. 23 vanadium, 1s2 is 2s2 2p6 3s2 3p6 3d3 4s2 argon is 4s2 3d3. 24 chromium, 1s2 2s2 2p6 3s2 3p6 3d5 4s1 argon, 4s2 3d5. 25 manganese is 1s2 2s2 2p6 3s2 3p6 3d5 4s2 argon, 4s2 3d5. 26 iron, 4s2 2s2 2p6 3s2 3p6 3d6 4s2 argon, 4s2 3d6. 37 cobalt, 1s2 2s2 2p6 3s2 3p6 3d7 4s2 argon, 4s2 3d7. 28 nickel, 1s2 2s2 2p6 3s2 3p6 3d8 4s2 argon, 3 4s2 3d8. 29 copper, 1s2 2s2 2p6 3s2 3p6 3d10 4s1 argon, 4s1 3d10. 30 zinc, 1s2 2s2 2p6 3s2 3p6 3d10 4s2 argon, 4s2 3d10. Problem 4.11. Write electronic configuration of 18 argon and 19 potassium using orbital notation and orbital diagram method. Solution. From atomic number, it is understood the 80 electrons are to be filled in argon and 90 electrons are to be filled in potassium atoms. These are to be filled in the orbital according to Earth-bound principle. The electronic configuration of this atom can be represented as 18 argon orbital notation 1s2 2s2 2p6 3s2 3p6. Then 19 K is 1s2 2s2 2p6 3s2 3p6 4s1. Problem 4.12. Find out one di-negative anions and one unipositive cation which are isoelectronic with neon atoms. Write their electronic configuration using orbital annotations and orbital diagrams methods. Solutions. Net has neon has Z equal to 10, therefore neon and its isoelectronic species contain 10 electrons each. The dinegative anionic species isoelectronic with neons is obtained by adding 2 electrons to the atoms with Z equal to 8. This is O2 minus. The unipositive cationic species isoelectronic with neon is obtained by removing 1 electron from an atom of Z equal to 11. It is sodium plus this species and their electronic configuration shown below. Neon number of electron 10. Orbital notation 1s2 2s2 2p6. Oxygen get 2 electron form O2 minus. Number of electron 10. Orbital is 1s2 2s2 2p6. Sodium 1 loses 1 electron and form into sodium plus 10 number of electrons. So 1s2 2s2 2p6.